Thank you for remembering to hit record, Najin. Starting over from the top for people who are tuning in and watching the recording. Today's Lunch and Learn is all about passive house development, why it's important, what it is, and why it's super relevant for House Our Neighbors, the work that we do, and for the future of our city. Yeah, thinking about preparing for this lunch and learn today, I think it's like well timed. Earth Day was just this past week. Um, and I think it's really exciting that in our work at House Our Neighbors, which is very focused on social housing, housing affordability, and making sure that Seattle, Washington, and the US are places where everybody can afford to live and thrive where they work in their communities and stay rooted in their communities. I think it's amazing that we also get to talk about climate resiliency, how to do our part to reduce our climate emissions, combat climate change, and make sure that as we're thinking about what our city is going to look like in the future, we also get to think about comforts, making sure that our environments are livable in heat and smoky environments, which are becoming more and more common. And so all of these are why it was very important for House Our Neighbors when we wrote Initiative 135, which created the social housing developer, that we wrote in a requirement that all social housing development is built to passive house standards. So it's something that we've been excited about and working on for a long time. But I'll say over the course of all that time, anytime I talk with somebody about passive house development and how we're excited that social housing is all going to be built to passive house, I almost never encounter anybody who knows what it is. So I'm very grateful that today we are able to put on this lunch and learn to talk about what this important piece of social housing is. And that we have Alexander here to share his expertise with us to teach us all about what passive house means. So Alex is an architect with 8 years of experience and has dedicated much of his career to advancing sustainable practices in his work. He brings direct experience from Passive House Project and a core living building challenges project. Driven by a passion for housing affordability, Alex is actively involved with the Democratic Socialists of America, very involved with House Our Neighbors, and the American Institute of Architects Committee on Homelessness. So, Alex, thank you so much for coming and teaching us all about Passive House today, and I'll turn it on over to you.
All right, thank you so much, Jeff. Go ahead and start this presentation. Present. Why is it doing that? Mm, 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 mm. Whoops. It is doing the wrong screen. Mm, 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 mm. Okay, still doing that for some reason.
We see the intro.
Oh, you do? I was giving, oh, it must be when, because it's showing me the next slide, isn't it, on the
Oh, it's
PowerPoint?
showing
I
you.
haven't done that before.
We
Okay,
see
great.
both the intro and the next slide.
Yeah, that's not what I want. I don't know how it's doing that.
Yeah, Alex, if you go back into that presentation and go into display settings, I believe you can do presenter view, which should allow us to just see a single slide and you can see your speaker view.
Okay, how about that?
Perfect.
Great. That is awesome. And I
Wow.
want
We
this
love
to
when we
be.
can phone a friend.
Yes, yes, we do.
Thanks for the audience participation.
All right. So thank you for everyone for joining us today. Before we dive into statistics of Passive House, I did want to also quickly kind of share a little bit about myself again on top of what Jeff was already sharing. So I graduated with a Master of Architecture from Kansas State University in 2017, where I also minored in Leadership Studies and Community Planning. I moved to Seattle because I was actively seeking out cities that were pushing the boundaries of innovative housing solutions, and I didn't believe that was going to happen in California at the speed that I craved. So as fate would have it, months after moving here, I stumbled upon the initiative I wanted to revive to create a social housing developer in Seattle. I was immediately drawn to its vision and have been involved in helping support this Seattle social housing developer ever since, including House Our Neighbors. So this journey from my academic background to my professional experience and my advocacy work with SHG and House Our Neighbors brings me here today to share this presentation with you. So, welcome to what I hope will be an informative yet fun session on the technical world of Passive House and why it's important to Seattle and social housing. Why will it be fun? Well, Passive House, in my opinion, is nothing less than one of the many necessary solutions required to save the world from climate change. Super important, which means we get to come up with fun, innovative solutions like Passive House. It's a topic gaining significant traction as we seek more sustainable and resilient building practices that aim to significantly reduce energy use. I've had the invaluable experience of working on a Passive House project in Burien, Washington, which came exceedingly close to meeting Passive House, except for the choice to install a more reliable, cost-effective mechanical system, which is still kind of a painful point with Passive House these days. With one specific component, prevented default certification, the entire process was still an incredible learning experience, where I got to see the important concepts of Passive House that were implemented in affordable housing projects. So we're going to do a little bit of interaction during this presentation. So we have some Slido questions. So if you just want to scan the Slido QR code with your camera, or if you can go to slido.com and enter that number, you should be able to participate and answer some of these questions. And as well as this being activated, you will be able to start entering Q&A questions on your phone, which we can get to towards the end of the presentation. See if we get a couple more people. Great. Okay, cool. So we have a pretty diverse range of people that are answering kind of a little bit of everyone. All right. Moving on. So what exactly is Passive House? At its core, it's a highly rigorous and systemic set of design principles. The standard is voluntary, but required in new buildings for the Seattle social housing developer. The primary aim with the standard is to achieve extreme levels of energy efficiency, dramatically reduce a building's energy consumption for heating and cooling, often by 75 to 90% compared to older buildings. This isn't just about saving money, it's about minimizing our environmental footprint. So this exceptional efficiency doesn't come at the expense of comfort. It's quite the opposite. Passive house buildings are renowned for creating incredibly comfortable indoor living spaces. This comfort is characterized by remarkably stable internal temperatures year-round, elimination of cold drafts, significantly improved indoor air quality, and quieter environment due to superior insulation and airtightness. It's a very holistic approach to building performance that prioritizes the well-being of its residents. One of the most compelling aspects of Passive House is its remarkable versatility and universality. It's not a niche standard for specialized residences. These robust principles can be applied to virtually any building type or scale, from traditional single-family homes to large apartment complexes, schools, office buildings, and even high-rises. This makes it a powerful tool for large-scale sustainable development and urban planning. The journey to modern passive house standards has roots that stretch back several decades, grounded in pioneering research and practical application, particularly in response to the oil crises of the 1970s. And today we face another US-made energy crisis, which I'll kind of touch on later. A significant and often cited precursor to Passive House is the Saskatchewan Conservation House built in Canada in 1977. The groundbreaking project was an early, ambitious attempt to create an ultra-low energy home, pushing the boundaries of insulation, thickness, and airtightness in passive solar design to radically reduce energy and heating and cooling. It demonstrated the immense potential for dramatically reducing reliance on active heating systems, such as furnaces, and served as a powerful proof of concept for the high-performance building movement. If a home in a frigid climate could consume ultra-low amounts of energy, then the same could be said of any home anywhere in the world. The official birth and formalization of the Passive House standard as we know it today occurred in Darmstadt, Germany in 1991. This project, which became the world's first passive house, was a result of a visionary collaboration between Dr. Wolfgang Feist, a physicist, and a Swedish professor, Professor Bo Adamson, of building science. They meticulously established the core technical criteria, focusing on energy, airtightness, and thermal performance that define passive house. It was not a one-off project. It was carefully monitored for decades, proving the efficiency and durability of the standard. Since then, it has been replicated and refined globally, demonstrating these principles are not just theoretical, but highly achievable and practical in real-world construction across diverse climates. To truly understand Passive House, it's essential to recognize that there's no single magic bullet or isolated technology that achieves the standard. Instead, it's a highly integrated, holistic design strategy built upon excelling in four fundamental control areas that define a building's performance. These pillars don't operate in isolation, they work together to create a superior building envelope and indoor environment. The building envelope it is essentially whatever component from the exterior. So the roof, outside walls, and the bottom floor that touches the heat flow, prevent unwanted heat loss in winter and unwanted heat in the summer. Air control, seen here, tiny air leakage, which are major sources of energy. Radiation control, which focuses on managing solar energy, harnessing daylight, and moisture control, critical for preventing water damage, mitigating mold growth, and ensuring healthy indoor humidity levels. Exploring the challenges they face and the innovative detailed solutions Passive House uses to overcome them. The first pillar, thermal control, is fundamentally about maintaining stable of weather extremes, be it a winter, scorching summer, or anything in between. The goal is to minimize energy required to achieve. Left illustrates a pervasive and critical flaw in conventional construction, which is the thermal bridging in these 2x6 studs. They act as bridges or direct thermal highways, allowing heat to bypass the insulation and easily escape the building in winter. One way to think about it is this. A solid object is denser than air. So then like the wood. So then it has more atoms per inch cubed. So I like to imagine that each atom has a bunch of heat with it. And so if you have more atoms with more heat, it's able to just push that heat through, which is why the studs here, and you see the concrete columns and concrete slabs on this concrete tower doing the same thing as well. So that acts as the bridge. It significantly undermines the overall effectiveness of cavity insulation, creating uncomfortable cold spots on the interior, increasing the risk of condensation, and leading to a lot of energy waste. So the thermal image of this home also illustrates that issue. The bright yellow and orange spots indicate areas of substantial heat loss from the interior, usually around the structural elements, as well as the concrete tower, which we see, meaning the structural system is not isolated from the exterior. The uncontrolled heat movement is just a massive heat loss, and that's something that Passive House aims to eliminate. So here, their solution is continuous insulation. It dramatically improves the thermal performance by implementing this 1-inch rigid exterior foam along the outside. As shown in the diagram, instead of relying on the insulation between the structural members, it's applied over the structural members and continuously over the roof. This effectively wraps the entire building in a thermally unbroken blanket, ensuring that no part of the structural frame directly connects the interior to the exterior. This critical continuous layer eliminates the thermal bridges that plague conventional construction, creating a much more consistent and effective thermal envelope. The result of this extra layer of design is evident in this after thermal image. You can observe a far more uniform and darker color across the building's exterior, indicating minimal heat loss and a consistent surface temperature. You can see a clear example of this home in the bottom right with very efficient walls, which are all blue. The windows are about as efficient as the home on the left, but the walls are much better. This signifies that the building's thermal performance is optimized, translating directly into vastly improved indoor comfort and the virtual elimination of cold spots and drafts. This fundamental shift from insulating between the structural elements to insulating over them is a cornerstone of Passive House performance, contributing to a more durable, quiet, and thermally stable indoor temperature. To achieve such robust thermal control, Passive House designers have a diverse and sophisticated palette of insulation solutions. Here it highlights all of these really common types, such as spray foam, fiberglass, cellulose, mineral wool, reflective, rigid foam board, loose fill, and batt insulation. I've highlighted cellulose, mineral wool, and loose fill as our favorites simply because they have less embodied carbon, if you are familiar with what that is. One particularly effective and increasingly popular solution for exterior continuous insulation is the mineral wool insulation, which is what it sounds like. It's a bunch of minerals extruded into a wool-like material. As you can see in the insulation image on the left, it's typically applied as dense, semi-rigid boards directly over the building's sheathing. The mineral wool offers excellent thermal performance, is naturally non-combustible, moisture resistant, and it provides good acoustic dampening. This continuous application is paramount to eliminating the thermal bridges and ensuring the entire building performs as a truly integrated thermal envelope. The image on the right shows one of my projects, which is also installing 1 inch thick mineral wool, which you see underneath this siding here. And this mineral wool on the left is about 2.5 to maybe 3.5 inches thick, which is pretty thick mineral wool. So we have a quiz to start. This question is compared to a typical new building, a passive house building likely uses how much of this insulation? And you might have to rejoin this quiz for some reason. Cool. We'll wait about until 10-ish people are able to give an answer.
I see some folks are maybe joining this from their phone. You can also just drop your answer in the chat
Sure.
if you can't do both. Brett says more insulation. I said less. We'll see who's right.
All right, we'll give 2 more people an answer.
Lil also guesses more. Ah, I'm bummed. I don't feel good about my odds.
The correct answer is actually generally significantly more insulation than your average building. In Washington, it might be only more insulation, but for a lot of other states, it's going to be in the significantly more category. So our next pillar is radiation control. This is all about intelligently managing how sunlight touches the building, harnessing its warmth and natural light when desirable, and effectively blocking it when it's not. It's a constant dance with the sun when it comes to architecture. The diagram on the left illustrates various architectural shading devices such as overhangs, strategic landscaping, horizontal louvers, and vertical screen walls. They're not decorative elements, they are precisely designed based on the solar angles throughout the year. Windows are traditionally the weakest link in a building's thermal envelope. Single pane windows are highly inefficient, acting as major conduits for energy loss. It's essentially even illegal, really, to even use single pane windows in new construction because the required insulation values for new windows are higher than nearly any single pane window can achieve. Passive house standards mandate exceptionally high performance windows, sometimes requiring triple pane, which feature multiple layers of low emissivity glass, which is like a special film on the glass. It also includes gas fills like argon and krypton that carry even less heat than just your typical air. These advanced windows dramatically reduce heat loss in the winter and unwanted heat gain in the summer, while also improving acoustic performance. Passive House takes a fundamental and intentional approach to building orientation from the very outset of the design process.
Hey,
And it,
Alex, really quick. When
yes,
you said improves acoustic performance, what do you mean?
good question. So acoustics would be the sound. So a lot of windows don't really do a good job of blocking sound, but thankfully, the more insulative a window is, the more it also blocks noise. Um, So this side here, it illustrates just the different shading configurations depending on which direction your building is facing, whether it's facing south, east, or west. Your shading device is going to be differently designed to take advantage of the sun when it wants to and block the sun when we don't want it. So these images here, they demonstrate how radiation control, the control of the sun, is not an afterthought, but an integral part of these buildings' architectural aesthetics and functional experience. They showcase real-world examples of thoughtfully designed external shading elements, such as these really large balconies on the right image that help prevent sun from entering the windows, but still getting plenty of light. Same with these interior courtyards, which allow a lot of light, but block direct light into the windows. So it helps get in light, reducing your actual lighting controls, but you're not going to overheat your spaces. Air control. The third critical pillar, and arguably one of the most defining characteristics of Passive House, is the control of the air. These technical mandates make buildings exceptionally airtight to prevent uncontrolled air leaks. This continuous green line in this diagram vividly illustrates the concept of the air barrier, a single continuous and meticulously sealed layer that completely wraps around the entire conditioned building envelope. This unbroken membrane acts as a definitive boundary, isolating the conditioned interior air from the unconditioned exterior air and moisture. It must be carefully designed to extend across all six sides of the building, including the floor, walls, and the roof. It's crucial because uncontrolled air movement through any gap, crack, or penetration is a major culprit in energy waste. It leads to uncomfortable drafts, allows outside pollutants such as dust, pollen, and volatile chemicals such as air pollution and any sort of other chemical to enter, and enables moisture to infiltrate and condense within wall cavities, causing potential damage and mold, and significantly compromise the effectiveness of the insulation that we talked about. By painstakingly sealing the building, Passive House eliminates these problems, ensuring consistent indoor air quality and temperature, and drastically reducing heating and cooling loads. Achieving such extreme air tightness, as seen in these images in one of my projects, it includes wrapping and detailing every single opening. This is where buildings are becoming more technical than they used to be. It involves the careful sequencing of materials, special airtight tapes, flexible membranes, and sealants applied at every single opening and seam. Every tiny gap, no matter how small, is identified and it's sealed. The standard of measurement for air control is air changes per hour. This changes this focus on air tightness is qualitatively measured by a blower door test, which puts a giant blower fan on the front door of a unit and just blows it in at a certain amount of pressure, which is called the air changes per hour. So to put this into perspective, that actually makes sense. Um, Washington State allows 4 air changes per hour for residential units. Most other U.S. states are typically in the range of 3 to 5. Florida just downgraded their standard from 3 to 7 air changes per hour, which is kind of on par with what they're doing these days. Um, the Passive House standard, though, is a mere zero point 0.6 air changes per hour, which is more than 6 times more airtight than the minimum required in our state. This extreme level of air tightness is a cornerstone of energy performance, but it also offers benefits like improved acoustic comfort, which means less sound from the exterior, reduced dust and pest infiltration, and enhanced structural durability because you have less water getting in. It also means, however, that one must be careful to select a contractor that can adhere to strict quality standards. Not every contractor is ready or prepared to meet the highly technical requirements. An unusual problem is the slamming door problem. While air tightness is a monumental advantage for energy performance, a very tightly sealed building can create an unusual side effect, creating differences in air pressure between rooms that can lead to doors slamming or becoming difficult to open. This diagram here highlights how various common building elements can contribute to uncontrolled air leakage in typical leaky construction. This is precisely why carefully designed and balanced mechanical systems are essential for Passive House. These sophisticated systems continuously bring in a controlled stream of fresh outdoor air, exhaust the indoor air, and crucially, these ERVs, which is an energy recovery ventilator, recovers about 80% of the heat from the air before it puts it outside of the house. So not only do these machines maintain perfectly balanced pressure throughout the home, but they also ensure exceptional indoor air quality. So we have one more quiz question. What elements are potential air leak risks in a typical building? Electrical outlets, light fixtures, windows, or all of the above?
We've got a lot of all of the aboves in the chat, Alex.
Nice. All right. You guys are all geniuses. It is all of the above. Pretty much anything that is in a wall is a potential air leak risk. You want the air that is in your current room to not leave the current room you're in unless it is particularly designed to do that. So that leads us to mechanical equipment to control air. With such minimal energy demands due to the superinsulated and exceptionally airtight envelope, passive house buildings can use smaller, efficient mechanical systems. The primary choice for both space conditioning, heating and cooling, and domestic hot water is almost always a heat pump system. And this is generally what they kind of look like outside of your house. And then this is the diagram seeing how it works from the inside to the outside. Unlike traditional furnaces or boilers that generate heat by burning fossil fuels, heat pumps simply move energy from one location to another. In winter, they extract the heat from the colder outdoor air, even the freezing temperatures, and transfer it indoors. And in the summer, they take the heat from the indoors and they dump it outside. This fundamental principle of moving rather than creating heat is what makes them so energy efficient. This diagram highlights how heat pumps provide both heating and cooling seamlessly. Here, this reversing valve simply just changes when you want to heat versus cool so that you can have the same system that can do both. Instead of, in a lot of our old construction, you have to have an air conditioner and a gas or a furnace separately. Those are two different systems. Here, this is just one. All right, and the last quiz question we have, which of these water heating methods aligns best with passive house principles? We didn't talk a lot about water heating, but I'm kind of curious if anyone can give a good guess. We have gas water heater, electric resistance, a heat pump, or an instant tankless water heater. Cool. This should be pretty, I think, an easy-ish one.
We're across the board.
Ooh, across the board. So the correct answer is actually heat pump water heater. The reason why the instant tankless would not normally be the best is because it is instant, it means you need either a high amount of electric resistance heating or a gas heater, which is kind of contrary to energy savings and not using fossil fuels in passive house. Electric resistance, while not using any fossil fuels, is just that generates heat, which means it generates more energy than a heat pump, which just moves heat around. Mackenzie, you did best. Nice. Moisture control. This is our final pillar. The moist final pillar is absolutely critical for the long-term durability, occupant health, and the structural integrity of any building. Its purpose is to manage and prevent water from entering or accumulating in unwanted places within the building. Uncontrolled moisture can lead to mold, rot, and degradation of materials, and even structural failure. This diagram of a brick veneer on the left highlights multiple sophisticated layers of the vents designed to handle moisture. No elements like the critical airspace behind the brick, which allows for the drainage and ventilation to dry out any moisture that gets behind the brick. Weep holes and flashing direct water out of the wall system. Beneath the cladding, like a plastic barrier essentially prevents moisture from getting into the sheathing and the framing. This multi-layered rain screen is what we call it. Approach ensures that even if some moisture gets into the screen, into the cladding, it is managed and safely given out of the wall, protecting the core structure. Similarly, the roof detail is the same. Illustrates best practices for shedding water effectively and preventing leaks. Now, the thing that Passive House really gets more into is humidity, the interior air of the units. So beyond just keeping the rain and bulk water out, moisture control is also about the indoor humidity and air quality. This kind of complex chart shows us what Passive House considers to be the comfortable range right here in this green area. So it wants to make sure that whatever your building is will always fit in this range. And so the systems, mechanical systems, your heating and cooling, your insulation, everything that goes into your building is calculated so that your building is always going to be in this little green area in the middle. Kind of a little bit beyond us as our architects, but that's why we have a lot of specialized engineers to help us calculate these humidity levels. Effective balance ventilation systems play an indispensable role here. They not only bring in fresh filtered air, they also actively help to control the moisture content, which removes excessive humidity or adds humidity in case it's too dry. So what does this holistic design strategy actually look like in practice? On this slide, you will see the 5 core technical principles integrated into every passive house building, each working in harmony to create the superior performance we've been discussing. Super insulation, thermal bridge free design, energy recovery ventilation with ERVs, which kind of take out they use the heat that's existing in the air, high performance windows, and air tightness. All are some of the most important criticals to the technical parts of Passive House. So now that we covered like really what is Passive House, I want to talk about why it matters. Um, so why this is most so critical and important is it goes far beyond just individual energy bills or personal comfort. It is a powerful, tangible, and scalable solution that addresses a multitude of interconnected global challenges we face, impacting our environment, our economy, our energy security, and our societal well-being. Passive House offers not just a better way to build, but a more robust blueprint for creating a more sustainable, resilient, and equitable future for all. This pie chart lays bare the sheer scale of global CO2 emissions, totaling a staggering 36.3 gigatons annually. When we talk about tackling climate change and decarbonization, we must strategically target the largest contributors, and the built environment, shown in black, really stands out. Building operations alone, the energy used for heating, cooling, lighting, and appliances, are responsible for about 27% of global CO2 emissions. This includes both direct emissions from fossil fuel in the buildings and indirect emissions from electricity that generates to power the buildings. Furthermore, when we account for the entire life cycle, including the energy-intensive production of building materials, the total contribution to the built environment reaches 42% of CO2 emissions. So Passive House directly targets and dramatically reduces the largest portion of these emissions by minimizing operational or energy demand. It's an essential strategy for decarbonizing our planet and achieving critical climate goals, adjusting both operational and by design, often leading to reduced embodied carbon through material efficiency. Diving deeper into energy uses within the United States, this chart clearly breaks down energy consumption across different economic sectors. It illustrates that the building sector collectively accounts for a whopping 40% of total energy consumption. This makes it a prime target for efficiency improvements. We can further segment this into 22% for residential buildings and 18% for commercial. This breakdown shows us that heating alone constitutes 31% of energy use, followed by cooling and water heating at both 12%. The implications here are pretty profound. By dramatically reducing the heating and cooling loads through its superior envelope and highly efficient systems, Passive House directly attacks the largest energy consumers within buildings. This leads to not only massive reductions in energy consumption and associated greenhouse gas emissions, but also significantly greater energy independence, reducing strain on national power grids and substantial operation cost savings for building owners and occupants. The relevance of Passive House
Hey,
extends.
Alex, really,
Yes.
really quick. I know we'll have Q&A in a sec, but there was a question in the chat for, do you know what wet clean is in that
In wet
breakdown
clean?
there? Wet
Oh, where
clean?
is that one
Yeah.
here? Um, I actually can't recall wet clean.
Huh. Something to Google and
Um,
report back on if anyone feels so inspired.
yeah, 5%. It's a decent amount for, as much as cooking. Um, Good question. So the relevance
Oh,
of passive.
I bet it's laundry instead of dry clean, like wet clean.
It could be. Yeah, maybe it's just dry cleaning, just not with the water heated that goes inside of it, Because we have
Anyway,
cooking, computers, refrigeration. So the relevance of Passive House does extend pretty far beyond energy statistics. It is a powerful and practical solution in confronting a series of global challenges. It offers tangible on-the-ground responses to several systemic issues. Firstly, it actively mitigates the escalating energy crisis by drastically reducing demand and prompting local renewable energy integration, lessening our reliance on volatile fossil fuel markets. I suspect that the recent US-made energy crisis will rapidly accelerate every nation's desire to decarbonize and free themselves from unreliable energy sources, and Passive House is a major part of that endeavor. Passive House is also a frontline defense against the climate crisis, directly addressing the largest source of greenhouse gas emissions through the built environment. Furthermore, it directly touches upon the food crisis by reducing energy demands that might otherwise compete with agricultural resources or require land for energy production. And critically, it plays a vital role in alleviating the housing crisis, promoting the development of durable, healthy, and affordable to operate living spaces, ensuring that high quality, sustainable housing is accessible to more people and is not just a luxury. This is especially critical when we consider the disproportionate energy burden on low-income households. will often spend 6 to 10% of their income on utilities, compared to about 3% for higher income groups. It is very common for market rate developers to install subpar mechanical systems to save money, but that results in higher energy bills for residents. Passive House dramatically reduces these costs, making true affordability a reality and a truly multifaceted response to a multifaceted problem. In an increasingly unpredictable world marked by escalated climate impacts, disaster resiliency is not just a benefit, it is a critical imperative for our infrastructure and our homes. Passive house buildings excel in this regard, offering a level of protection and stability that conventional buildings simply cannot match. One of the most critical advantages is the ability to maintain incredibly stable indoor temperatures for extended periods of time, even when the power grid fails or during severe extreme weather events. Imagine this scenario. During a summer heat wave, the super insulated and airtight envelope of a passive house building, can remain comfortably cool for several days without any air conditioning, providing a safe refuge and preventing dangerous overheating. Conversely, during a winter ice storm or blizzard, the building can retain its warmth for extended periods without needing a furnace, protecting occupants from dangerously cold conditions and preventing pipes from freezing. This ensures that continuity of care for medications, preserves food, and reduces the strain on emergency services. This robust passive survivability means that passive house buildings are not just energy efficient, they are also safe and reliable havens during grid outages and escalating climate-related disasters. This graph here on the left provides a compelling data-driven evidence of the dramatic energy savings delivered by passive house in real-world applications. It compares the specific annual heat consumption of typical low-energy homes in Germany with various passive house settlements. The visual disparity is pretty striking and consistent. The passive house projects here on the right, this one, and this one, achieve significantly lower energy levels than the ones on the left, which are still considered low-energy homes. Obviously, you have some energy homes that are really low energy. Maybe they like it cold, and you have some that use a lot of energy. Maybe their TVs are always on and they like their house hot. But regardless, the average, even over here on the right, the most energy intensive homes of passive house homes are still lower than the lowest energy house of typical construction. So it is pretty remarkable how much of a difference passive house makes. To kind of see that, I also made this little diagram. Um, it shows a single building compared to typical code minimum conventional standards consumes roughly the same amount as roughly 4 to 5 buildings of passive house combined. So this is not a minor incremental improvement. It represents a fundamental paradigm shift in building performance and energy efficiency. Imagine the profound collective impact if every new and existing building adhered to passive house principles. We would drastically cut national and global energy consumption, significantly reduce our carbon footprint, and create a far more sustainable, resilient, and less energy dependent built environment. Energy can no longer be seen as an infinite resource, but as something to cherish and handle with care. So, what are your takeaways from this presentation on Passive House? You can choose more than one. Hmm, interesting. Although it seems like it keeps kicking everyone off every time a new question comes up.
In the chat, we got passive house is a crucial standard and essential for climate goals. You could also, in your mind, label them as 1 through 6, with 1 being passive house is essential and more informed on requirements being 6. And you could put that in the chat.
Mhm.
We got it's essential. We got it's
Control.
crucial.
Seattle needs this standard, more informed, and essential for climate goals. Nice. Okay.
That you
So,
truly quantify everything. Oh, I like that.
nice. I like that. So, great. Now that we understand the profound benefits and the urgent need for Passive House from a global and a technical perspective, let's bring it home and focus on our local context. Seattle has a unique opportunity and I believe the necessary drive to truly lead the way with Passive House adoption in a meaningful and impactful manner. After all, Seattle has committed to achieving net zero carbon by 2050 as part of our climate action plan, and buildings are critical to meeting that goal. Specifically, the Complete Communities Coalition has a proposed comprehensive plan amendment, making the path significantly easier and more accessible for key players in our community, such as the Seattle social housing developer who requires Passive House. By actively providing strong incentives, we can empower organizations to seamlessly integrate Passive House standards into their projects. So this gets a little bit more complicated, and we'll see, even this took me a hot minute to kind of wrap my head around. But one of the most impactful and tangible mechanisms currently being discussed is a height bonus for passive house projects that exist in urban and regional centers, neighborhood centers, and transit and park-oriented corridors. Urban and regional centers are shown in these brown area here with the 85 feet being proposed, and the neighborhood center are these blue areas with the 75-foot height proposed. Existing over here on the right is at 32 feet, 50 feet, and 80 feet. So we have some overlap here, which gets a bit complicated, but essentially you can see that in some of this urban area for Roosevelt, that there are some pretty low heights that are currently existing at 32 feet and 50 feet. So this essentially would be a big bonus from 32 feet to 85 feet for some of these zones.
Can I really quickly, can you head back to that slide really quick, Alex?
Yes.
Um, yeah, I just wanted to pop in here and say these are like our draft proposals that we're putting forward, and we are still like working with folks to like figure out if these are the right numbers. For example, that 55 in transit and park-oriented corridors that actually go up another 10 feet.
Mm.
So we'll kind of see. We might like round around and figure out as we talk with more folks who will be working on this what is really going to allow for social housing and passive house to really be incentivized to the point where it's like built at scale.
Yeah, thank you so much for that. That's actually great. Yeah, because this is just from the current stuff. And so that is currently in flux. So if anyone has any comments, I'm sure we'd love to hear them. And why does height matter? The answer is pretty straightforward. More height directly translates to more units on the same land footprint. The benefits of this increased density are pretty interconnected. By accommodating more people closer to jobs, services, and amenities, enable shorter commutes, reducing individual vehicle miles traveled, reduces traffic congestion, and related emissions. In the increased height fosters reduced car dependency, making public transit, biking, and walking more viable and attractive options. Most importantly, by strategically accommodating more people within our agricultural land, wildlife habitats from the irreversible features of sprawling development. Relying on existing utility infrastructure that is required in sprawl is a huge concern for cities trying to reduce their liabilities. This diagram illustrates the efficiency of vertical growth. The building on the left is a single lot able to use 6 units in a 3-story building, where an 8-story building on the exact same footprint can provide 16 units. That is a huge bonus.
And if I could also add on the affordability piece for this, like think about like that piece of land, that one unit costs, let's say $1 million to buy. And then the elevator shaft is like very expensive and the roof is very expensive. So the cost of building each of those units overall is much higher. Than if you spread out the same cost to all these other units, while it is more expensive to build, what, 8 stories instead of three, the cost per unit is a lot cheaper. And for the social housing developer, the cost of rent is going to be like largely dependent on the cost of the unit. Like the social housing developer is just trying to break even on costs. And so if the cost for building your unit is cheaper, it means your rent could be even cheaper, which is,
Mhm.
of course, the desired outcome for everybody.
Yes. Thank you. And then one of my last slides, this is just a visual summary of the smart policies like the passive house height bonus. On one side, you see the direct consequence of unchecked low density development and sprawl, single family homes dividing a pristine forest. The model consumes vast amounts of undeveloped land, encroaching on critical natural habitats, fragmenting ecosystems, and requiring extensive, costly infrastructure per capita, more than any of those homeowners can afford in their taxes. It's an unsustainable development pattern. On the right, we see the intelligent, sustainable alternative. Dense, well-planned urban development like the affordable housing apartments, Cedar Crossing, and Roosevelt, Seattle. By building vertically and concentrating housing in existing urban centers, we can accommodate a growing population while simultaneously preserving critical green areas, forests, agricultural lands, and wild areas that are vital for biodiversity, carbon sequestration, and quality of life. This is the direct, conscious choice we make with our zoning and development policies. Either we continue to expand outwards with unsustainable impacts, or we build smarter, more sustainably, and more equitably within our existing urban footprint with these passive house amendments. So we've covered a lot today, moving from the technical details of Passive House to its profound global impacts and our local opportunity here in Seattle. As we conclude, I want you to see that this isn't just a theory or concept, it's a proven reality happening now in major cities like New York and Boston. On the right, we see the world's largest passive house building, an office tower in Boston. And on the left, we see the tallest residential passive house building in New York at Cornell Tech. Passive House promises homes that offer unparalleled comfort, promote health through superior air quality, and provide critical resilience during increasingly common extreme weather events and power outages. It's the most powerful tool we have to drastically cut energy consumption, directly confronting the climate and energy crises. By embracing Passive House principles, especially through initiatives like the Seattle Social Housing Developer, we can ensure that high-performance, low operating cost housing is accessible to everyone, not just a privileged few. Seattle has a unique chance, and I believe the collective will to help lead the nation in this movement, to build a city that is both dense and green, vibrant and resilient, and fair for all its residents. Your engagement during this lunch and learn today is the first step. The next is to translate that understanding into action. Your voice is incredibly powerful in shaping our city's future. By supporting this proposed comprehensive plan amendment and advocating for these changes, you become an active participant in building this better future. This isn't just my vision, it's our neighbor's vision. It's a vision future we can truly can and must build together. It's all of our visions. So here are some other examples of passive house projects in the US, and Boston is pretty much seemingly leading the way. There's a lot of homes in Massachusetts and Boston. We got these cute ones. This didn't even a name, it's just a house. We got some good-looking places in Boston, little trendy. And then we got some larger ones here in Portland and in the Bronx. These are all passive house projects, all finished within the last 5-ish years. So it's definitely gaining traction, and I'm really excited to see where it goes. Thank you.
Amazing. I see folks already clapping. Let's virtually give it up for Alex. Thank you so much for putting together such an informative presentation for us. I feel like I've learned a lot about Passive House over the years, and I still learned a ton more. In particular, I really didn't fully understand what thermal bridges were before this presentation, but now I feel like I have it on lock.
Nice.
Um, yeah, so I really appreciate it. Thank you so, so much. And I really appreciate also the comprehensive view on like why this is so important. Lil asks if this recording will be somewhere. Yes, it will be on How's Our Neighbors YouTube channel. With the recording, Nishin, do you want to stop it here? So we're going to stop.